How a constant speed propeller works. Part 1. How to use a constant speed propeller. Presented by Carl Valeri. You can find notes for this video presentation at expertaviator.com. I had a question from one of our readers who wanted to know how a constant speed propeller works. Well, before we learn about how a constant speed propeller works, first let's just discuss propeller basics. The propeller converts rotational power from the engine into thrust. What a constant speed propeller does is it's a device which allows us to efficiently convert power from the engine into thrust. Let's look at the design of a propeller blade. The propeller blade is actually similar to a wing of an airplane, except that it rotates around a center hub. Similar to a wing, the propeller's chord is an imaginary line drawn from the center of the leading edge to the rear of the propeller. The blade angle is a measurement of the distance between the propeller chord and the plane of rotation, which is fixed in one position on most airplanes. When we speak about propellers, though, we don't talk about the blade angle, we talk about the pitch of the propeller. Propeller pitch is the distance in inches in which the propeller would screw through the air in one rotation. When changing the blade angle, we change the pitch of the propeller and use the term controllable pitch propeller. Therefore, when we change the blade angle, we are changing the distance the propeller would screw through the air, or are controlling the pitch of the propeller. That's why we call it a controllable pitch propeller. So, why would we use a constant speed propeller? Well, like we said before, it's to make the propeller more efficient, use it more efficiently. Most of these single-engine aircraft are equipped with a fixed-pitch propeller, which is efficient at some specific forward speed. Normally, the propeller design of a fixed-pitch propeller is a compromise of efficiency between cruise and climb. The reason a propeller is most efficient at a specific speed through the air is due to propeller slip. Propeller slip is the difference between the theoretical pitch, or geometric pitch, and the actual or effective pitch of the propeller. An efficient propeller is one in which has the least amount of slippage and therefore converts more engine power into thrust. A constant speed propeller keeps the propeller pitch adjusted for maximum efficiency for most conditions of flight. So let's talk about the different realms of flight and the blade angles. Most of these aircraft are designed to have a blade angle for different types of aircraft that we would fly. For instance, like a fixed, a retractable, turbo. And the pitch range on these propellers goes from, say, a low to a high of a certain number of degrees. Most of them are around 11 to 26 on the airplanes that we fly. But in transport category, they can be very low and go to a very high pitch setting. To understand a propeller, a constant speed propeller, we need to first understand what the manifold pressure gauge is. And the manifold pressure gauge, if you just understand that, and this is one instrument that most people get confused on, that it measures absolute pressure from the intake manifold. Okay, absolute pressure from the intake manifold. It reads ambient pressure when the engine's not running, of course. And as the throttle is closed, pressure decreases. So cylinders demand the same volume, creating a negative pressure in the manifold as the throttle is closed, and as the throttle is open, the absolute pressure increases in the manifold, therefore increasing the manifold pressure as we open the throttle. Let's take a look at this. Here are the cylinders, the intake and also the throttle. So think of both, the cylinder and the throttle, and the volumes of air that pass through each. The manifold pressure is again measured on the intake manifold here. As the cylinder moves downward, it creates a vacuum, or it'll pull that volume of air through. The throttle, of course, does not allow air, all the air it can through there, the ambient air pressure, it actually chokes off some of the air. In other words, almost starving the engine, even at idle thrust, or idle power, excuse me. So as we throttle the engine, the actual cylinder is going to pull down and create a vacuum within the intake manifold. Therefore, our pressure in the intake manifold is usually a negative compared to the outside. It's less than the outside pressure. And that is where we measure our manifold pressures, at the intake manifold. We'll look at this again later when we decide to set our cruise power in flight. But let's first take a look at our takeoff configurations. During takeoff, we need most of our power converted into thrust. You know, remember, we're not moving through the air very fast, and the low blight angle does a few things. First, it keeps the angle of attack small and efficient with respect to the relative wind. Second, the engine turns at a higher RPM and converts most fuel into heat energy for a given time. And third, the low pitch causes a smaller mass of air to be handled by the propeller, but the high RPM and slow speed causes a maximum thrust. So when you're taking off, before you take off, you've set your RPM to maximum, and you push the throttle, usually full forward, on a non-turbocharged engine, and you watch your manifold pressure gauge for your power. Now, after you've taken off, you want to set your power for your initial climb. The speed of the airplane increases and automatically changes to this higher angle during the takeoff roll. Again, greater pitch. And what we're going to do here is we're going to set first our power after the initial climb. We're going to set our manifold pressure. Normally in most aircraft, especially non-turbocharged, we want the manifold pressure to be less than, quote-unquote, the RPM. In other words, if we're going to climb, it's usually the climb setting is 25 inches or 24 inches of manifold pressure and 24 or 25 inches of RPM. So again, we first set our manifold pressure and then our RPM on the initial climb. Let's take a look at cruise and how we set our power for cruise. First thing we have to do is a little bit of planning before we take off, and we look at what pressure altitude we want to fly at for the winds, and also, say, for the temperature for that day, and also for weather. We've chosen a pressure altitude of 4,000 feet. We also know that we like to cruise at about 2,300 RPMs because that's most comfortable for us in the airplane and creates less noise. And at that RPM setting, we also want to burn approximately 12 gallons per hour, which would produce about 69% power on that aircraft and give us a true airspeed of 133 knots. To get this cruise speed, power, and fuel flow, what we'll do is we'll first set our manifold pressure to 22. So again, let's take a look at this. We set our manifold pressure first at 22 inches. Then we set our RPM at our 2,300, which is what we wanted to set. But something else interesting happens. We have to go back and reset our manifold pressure, because what happens is when you bring the RPM back, the manifold pressure rises a little bit. So why do we have an increase in manifold pressure when we decrease the RPM? Now let's go back and review the manifold pressure and what the manifold pressure is reading. Again, looking at our cylinders and looking at our carburetor and our intake, let's take a look at how we're reading that manifold pressure. Again, the manifold pressure is the absolute pressure in the intake manifold. So when the cylinder is moving, it's sucking air out of that manifold, creating a negative pressure within that manifold, a suction or negative pressure or a vacuum. When you begin to actually close the throttle, you're actually going to choke off the engine a little bit. But when we increase our RPM, when we decrease our RPM, we are moving that cylinder at a much slower rate. Therefore, less air is being sucked into the piston, or excuse me, into that cylinder. Less air is being sucked into that cylinder. So therefore, there is a lower negative pressure. Therefore, our manifold pressure actually would start to increase a little bit once we set our RPM setting. So again, we look at our intake, and we've already changed our throttle setting. We changed our RPM, and now we have less air being pulled through because of less RPM into the cylinder. Therefore, the manifold pressure would actually go up. And we know that because the manifold pressure is measured in the intake manifold. And this is a tough concept. So if you could just look at that again over and over, and then know that, you know, when you decrease the RPM on this engine, there's going to be less air being pulled into the cylinder. Therefore, we will have less of a vacuum, less of a suction, and the pressure increases in the manifold. Okay, say we've been cruising along, and the next thing we want to do is we want to actually increase power to climb. Well, before we increase power, the first thing we want to do is we want to increase the RPM on the aircraft so we don't over boost the engine or increase the manifold pressure too much. And that'll actually decrease the heat and the pressure on the cylinders. So what we'll do is first set the RPM, then we bring our power up using our throttle and bring the manifold pressure up to a good climb setting. Normally you're looking at, say, 24 or 2500 RPMs, and a climb manifold pressure of, say, 25 to 24. Now on the descent, it's much easier. We've already set everything up for cruise, and we have our RPM setting that we like for cruise. We're fairly quiet. So really all we need to do is pull back on the throttle and decrease our manifold pressure. Remember, what are we doing? We're throttling back, we're choking off some air, and actually creating more of a vacuum inside the intake manifold. Therefore, our manifold pressure is going to drop. Now, during landing, we're doing the same thing. We're bringing our power back using the manifold pressure, but we're also going to increase our RPM. Now, remember from that chart, I showed you that there is a specific blade angle, a low pitch stop, where you will actually, the mechanically will stop the blade from actually going to a lower and lower pitch. And if you really concentrate and you know what speed of your aircraft will allow you to put the propeller full forward without seeing a change in that RPM, you'll actually really impress your passengers, I think, because they won't notice any change in pitch or any change in the RPM of your aircraft, because you're at a slow enough speed that, remember, that constant speed prop is still it's going to continually, as you slow, it's going to decrease that pitch. And now when you bring the propeller full forward to decrease that pitch, oh, look, now there is no change. So during your landing, people won't even hear the difference. So that's a quick overview of how a constant speed propeller works. I hope you enjoyed this presentation. And if you look at expertaviator.com, there is a full description of how a constant speed propeller works, and also some links to other websites where you can get some really good information on how to use a constant speed propeller. This is Carl Valerian. I hope you have enjoyed this presentation.